functions. So we're moving into a new topic today. It's still part of chapter 3, but we're done with talking about polynomial functions, and we're going to talk about rational functions. So a rational function, the root of the word rational is the word ratio. So a rational function is a ratio of two polynomial functions. Okay, so that is, a rational function is a function that can be expressed as p of x over q of x, where p and q are both polynomials. And q can't be 0, obviously. Can't have 0 in a denominator. So here's an example of a rational function. X squared plus 5x plus 8 over x times x minus 4 times x plus 2. So my numerator is a polynomial expressed in like the standard polynomial form. And my denominator is a polynomial expressed in factored form. You can use either way of expressing it. All right, so the domain of a rational function is all real numbers, except any x values that will make the denominator 0. So for this example rational function, what values would make the denominator 0? 0, yep. So x cannot be 0. What else? Positive 4 or negative 2. If I plug in any of those values, I would make my denominator 0. So if I was going to write my domain in interval notation, I would start as far left as I can, negative infinity. And then I would put comma and go up to the smallest x value, which is negative 2, right? And then put an open parentheses, because that means don't include the negative 2. And then I would union that with negative 2, right? But not including the negative 2, up until 0. Don't include the 0, because I can't put 0 in. And then union that with 0 to 4. Don't include either. And then union that with 4 to infinity. Good. All right, so there are 3 x values that we have to exclude from the domain. Okay. Let's investigate what happens near a value that's excluded from the domain. We know that you can't plug the value in itself, so the function has no value there. But I want to know what happens near it. So we're going to start with the simplest rational function, which would be 1 over x. Okay, what value of x is excluded from the domain of 1 over x? 0. That's my excluded value, 0. I'll just write 0. Yep. All right, I want to fill in this table of values to see what happens to the y values of f of x equals 1 over x as the x values get closer to this excluded value of 0. So I'm starting at 1, like that's kind of close to 0, right? 1 integer away. So if x is 1, what is f of x? 1 over 1 would be 1. And if x is a half, what's 1 divided by a half? No. 2. 1 divided by 1/2. How many times can you put 1/2 into 1? 2 times. So, and if 1 divided by 1/2, instead of dividing, think of that as multiplying by the reciprocal, 2 over 1, right? And you get 2. How about 1 divided by 0.1? 10, yeah. 1/10 goes into 1 10 times. And 1 divided by 0.01, 100. 1 divided by 0.001, 1,000. 1 1,000th can go into 1 1,000 times. All right, so in this table, my x values are approaching 1 from the right side of 0. So if you picture a number line, right, here's 0. I started with 1, and then I went 1/2, and then I went 0.1, and I got closer and closer to 0, moving through numbers from the right of 0. Okay, so we say where x values are approaching 0 from the right. So as these x values approach 0 from the right, what's happening to the y values of the function? They're getting bigger, yeah. They are approaching infinity because they just get bigger and bigger. When you make your denominator smaller, it makes the value of your fraction bigger, right? Because if you divide by a smaller number, it will go in more and more times. So some shorthand notation for this English sentence that we wrote here. We said as the x values approach 0 from the right, so these x values are getting closer and closer to 0 from the right side of 0. The values of f of x approach infinity because they're getting bigger and bigger. And then the shorthand notation for that sentence is we use arrows. When you see an arrow, you can read that as the word approaches. So this says as x approaches 0, and that little plus sign means from the right, like through positive values, yep. If I put a little minus there, it would mean from the left. So this says as x approaches 0 from the right, f of x approaches infinity. So it's just a direct translation from what we wrote in English using some notation. All right, in this table, my x values are approaching 0 from the left. So I'm starting at -1, and my x values are getting closer and closer to 0. So if you picture a number line, here's 0. I'm starting at -1, and I'm getting closer and closer to 0, but I'm heading towards 0 from the left side of 0. So if x is -1, what is 1 over x? -1. 1 over -1 would be -1. What is 1 divided by -1/2? -2. 1 divided by -0.1? -10. -100. -1,000. So in this case, as the x values approach 0 from the left, so as these x values are getting smaller and smaller and smaller, getting closer and closer to 0, what is happening to the values of f of x? They are approaching -infinity. So the shorthand notation for that sentence is as x approaches 0, read the arrow as approaches, and this little negative sign means from the left. So this says as x approaches 0 from the left, f of x approaches -infinity. So as x approaches 0 from the right and the left, it's growing, it's getting really big as we approach from the right and really small as we approach from the left. So as the x values are approaching 0 from the right side of 0, yeah, so we're approaching 0 from the closer we get, the bigger the y values get. When we're approaching, here's 0, approaching 0 from the right, the y values go to infinity. And when you approach 0 from the left, so move to the left side of 0, as we head towards 0, the y values approach -infinity. So what we have at 0 is a line that my graph is approaching and getting closer and closer to, but never touching, and we call that a vertical asymptote at that excluded value from the domain. We said the function's not defined at x equals 0, and it turns out that what happens when you get near 0 is the function gets really big or gets really small, and you have a vertical asymptote. All right, so now we know what happens near x equals 0, right? So I kind of drew what happens near x equals 0. I kind of know, like from -1 to 1, I kind of know what happens. But I want to find out what happens elsewhere. Analyze the rest of the behavior of the graph. All right, so does 1 over x have any x or y intercepts? Well, to get a y-intercept, we would evaluate f of 0, and you can't do that. It's undefined. And to get an x-intercept, we would set the function equal to 0. Right, and if I say I cross-multiply this, I would get 1 times 1 equals 0 times x. There's no x value that will make that true. So we have no x-intercepts and no y-intercepts. All right, so let's think about the end behavior of this function. What happens as x gets really big? As you plug bigger and bigger values of x into this denominator? It gets smaller, yeah. So if I plugged a 10 in for x, I would get 1/10. If I plugged in 100, I would get 1/100th, which is much smaller, right? If I plugged in 1,000,000, I'd get 1/1,000,000th, which is teeny tiny, right? So I could say, as x approaches infinity, f of x approaches what? 0. Yep. It gets teeny, 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 but it never gets smaller than, never gets negative, right? No matter what I plug in for x, this value of 1 over x will just be closer to 0. Right, so that's the end behavior to the far right. What about as x approaches negative infinity? Also approaches 0, yes. Because my denominator is still getting really big. My numerator is staying 1. Bigger denominator makes a smaller fraction. So it is approaching 0. It's just that it's approaching 0 negatively. Right? The values of the function are negative if I'm plugging in negative x's. And the values of the function are positive if I'm plugging in positive x's. So it approaches 0 on both the far right and the far left. And what we use to describe the end behavior of a rational function, if it approaches a specific value at the far right and the far left, we say that we have a horizontal asymptote. So if f of x is approaching 0, then the line y equals 0 is my horizontal asymptote. My graph approaches that line at the far right and the far left. Just a line that the graph approaches, gets close to. Think of it like a guideline when you're trying to draw the graph, which we will do now. So I know we have a vertical asymptote, which I'll do in one color, at 0, right? I know I have a vertical asymptote here. This is a line. My graph is going to approach but not cross. And then I have a horizontal asymptote at 0, so I'm going to put in a horizontal line. But for horizontal asymptotes, they only govern end behavior. So I'm only going to draw the horizontal asymptote at the far right and the far left. I'm not going to connect it in here. Because when I say an asymptote is a line that the graph approaches but never crosses, I can break that rule for horizontal asymptote. I might cross it in the middle. It's only the line that the graph approaches in end behavior. We'll see some examples. You'll see what I'm talking about. All right, so then I might plot a couple of points. I know that when I plug in 1, I get 1. When I plug in -1, I get -1. And then my graph is just going to approach its asymptotes. That's what rational functions do. They just approach their asymptotes. So once you know the asymptotes and maybe the x and y intercepts if it has any, then you just need a couple of points and your asymptotes guide where to draw the curves. What kind of symmetry does this graph display? Origin symmetry, yeah. Right, if I folded it over the x-axis and the y-axis, the two graphs would be on top of each other. That's called origin symmetry. So how do you confirm origin symmetry algebraically? We can look at it and see that it looks like it has that symmetry. How do you do it algebraically? Do you guys remember? We have to evaluate f of -x, right? if f of negative x equals f of x, then we have y-axis symmetry. And if f of negative x is the opposite of f of x, the exact opposite, then you have origin symmetry. So basically, you plug negative x into your function, and if you can get f of x or negative f of x out, then you'll have y-axis or origin symmetry. So let's look at our function 1 over x. So in this case, f of negative x will be 1 over negative x. Is that the same thing as f of x? Is it the negative of f of x? Yes, because I can put a negative sign anywhere I want for a fraction. I could write this as negative 1 over x, which is negative f of x. So if I have f of negative x equals negative f of x, that means I have origin symmetry. All right, so this graph, 1 over x, is a new parent function that you should have in your mental catalog of parents, like functions you just know what their graphs look like y equals x squared, y equals x cubed. What else do we know? Y equals the absolute value of x, y equals the square root of x. So you should have sort of a mental inventory of several functions you just know what they look like. This should be one that you add to it. And then, since this is a parent function, we can just shift it around in the plane by using transformations. All right, so here's another parent function, f of x equals 1 over x squared. What value is excluded from the domain of this function? 0. Can't put a 0 in there, it would make the denominator 0. Let's use arrow notation to describe the behavior of f of x near 0. So I want to know, as x approaches 0 from the right, f of x approaches what? And as x approaches 0 from the left, f of x approaches what? Infinity, yes. On both of them? They're both infinity, yeah. So if I were to plug teeny tiny values, like close to 0, like 0.1, 0.01, 0.001, into this function, 1 over x squared. Well, when you take a small number and you square it, it gets even smaller, right? Like 0.1 squared is 0.01. So I'm plugging in a small x value, I square it to make it even smaller, and then you do 1 over that thing and whoosh, it blows up, right? It's going to get huge. So as I approach 0 from the right, f of x is going to approach infinity. And as I approach from the left, because I'm squaring, it's still positive, because when you square a negative value, even though we're plugging in negative x values, things to the left of 0, I'm going to square them, which makes them positive, so my fraction's still going to blow up. Yeah. That's okay. So, right, that's what you said, but that was wrong. Yeah. Because when you put a negative value in for x, and then you square it, you get a positive, because negative 0.1 times squared is negative 0.1 times negative 0.1, which is positive 0.01. Yeah, so when you square things, you can only ever get a positive answer. All right, so we know the behavior near the excluded value, so we've got a vertical asymptote at this excluded value of 0, and my function blows up when you come from both sides. All right, so now I want to describe the end behavior of 1 over x squared. So I want to know, as x approaches infinity, f of x approaches what? And as x approaches negative infinity, f of x approaches what? 0, yeah. As x approaches infinity, you're going to be plugging really big numbers into this denominator, and 1 over a really big number is a really small number, right? So these values of the whole fraction are going to get teenier and teenier and teenier as the number you plug in gets bigger and bigger and bigger. So it approaches 0 at the far right and the far left, which means I have a horizontal asymptote at y equals 0. Does 1 over x squared have any x or y intercepts? No, for the same reason as 1 over x. I try to plug 0 in and I can't, so it has no y-intercept. I try to set it equal to 0, and I end up with an equation that has no solutions. All right, so now I would like to sketch a graph of 1 over x squared. And I know I have a vertical asymptote at x equals 0. This is my excluded value of the domain. And a horizontal asymptote at y equals 0. And I know that when I approach 0 from the right and from the left, from either side here, as I head in towards 0, the graph shoots up. And then I know as I head out towards the right and towards the left, the graph is supposed to come down towards 0. And it should go through the point 1, 1, so I drew this badly. Okay, so 1, 1, 1, 1. When you plug in 1, you get 1. When you plug in -1, you also get 1. And then it should shoot up towards infinity as I get close to 0, and head out towards 0 as x goes to positive and negative infinity. Now the asymptotes I drew, those are just guidelines. They're not actually part of the graph. Does this appear to have any symmetry? Y-axis symmetry. Yes. To confirm it, I'm going to have to evaluate f of -x. Yeah. And if I have y-axis symmetry, when I evaluate f of -x, I should get f of x back. So if I plug a -x into this function, I get 1 over -x squared. But -x squared is the same thing as positive x squared. Because when you square a negative, negative times a negative gives you a positive. And 1 over x squared, that is my function. That is f of x. So I do have y-axis symmetry. So this is another new parent function that you should add to your list of your mental list of functions whose graphs you know what they look like. And now I want you to work in your groups for a bit on transforming these new parent functions. We're going to just shift them around in the plane, figure out where the asymptotes are, x and y intercepts. So there's a bunch of questions to help you, and then you're going to sketch the graph. Sure. Just the symmetry part, or? Okay. All right, so to go over this first one, oops. All right, I want to transform the graph of 1 over x or 1 over x squared, right? So I've got 1 over x minus 5. What's the parent function for 1 over x minus 5? 1 over x. Good. Now, that minus 5, is that an inside change or an outside change? Inside. Great. It's a minus 5 inside, so what kind of transformation am I going to have? Right 5 units, right? So if you think about what 1 over x looks like, we should have a mental picture of 1 over x that looks like this. I just need to shift it right 5 units. So before I do any of these answers, I could just draw the graph. I'll put an asymptote at 5 instead of at 0, right? Because I used to have an asymptote On the y-axis, shift it right 5. And then I still have an asymptote at 0. And here's my graph. Well, actually, I should be more accurate, a little bit more accurate. Because my old graph used to go through the point 1, 1 and 1, -1. So I just shift those points to the right 5 units, and then have your graph approach its asymptotes. Yes?
So is it going to be like everything that we do is a
Mm-hmm.
relation to that?
Yes. Yes. So you can just shift the graphs that you know what they look like. You know what their asymptotes look like. You know what the behavior is near the asymptotes. You can just shift them around. So now that I've drawn a sketch of the graph, answering these questions is going to be a lot easier, right? Though you could answer the questions and use them to draw the graph, which is what we did earlier in class before we knew what anything looked like. So what's the domain of this function that I just drew? Yeah, it's going to be all real numbers except for 5, right? Because 5 would make my denominator 0. And I can look at the graph and see, oh yeah, it lives on all real x values except for 5. There's no function value at 5. So I'm going to write this as -infinity to 5, union 5 to infinity. So the value that's excluded from the domain is 5, which means I have a vertical asymptote at x equals 5. And you can see it in the graph here. X and y intercepts, none. If I, oh, sorry, that's not true. There's a y-intercept, because if I plug 0 into f, I get -1/5. So here's my y-intercept. It does cross the y-axis, and that point is at -1/5. Y-intercept, no x-intercepts. Okay, so my behavior near the vertical asymptote. So I want to know what happens as I approach 5 from the right and from the left. So I'm going to say as x approaches 5 from the right, f of x approaches. So here's 5. Go a little bit to the right of it. As I head towards 5, as my x values head towards 5 from the right side of 5, the y values go towards infinity. And then as x approaches 5 from the left, f of x approaches. So this time, start at 5, go a little bit to the left of 5, and then follow the graph towards 5, and the y values are going to -infinity. And then end behavior, as you go to the far right and the far left, on both ends, what are the y values approaching? 0. As I head out towards the far right and towards the far left, my function is approaching the x-axis, which is a y value of 0. We'll say as x approaches plus or minus infinity, f of x approaches 0. And then that means that I have a horizontal asymptote, the line y equals 0. And then does this appear to have any symmetry? No. And I can check by just doing f of -x, which is 1 over -x minus 5. That is not the same as f of x or the opposite of f of x. Do you think that'll help you do the rest of them? Okay, good.